In this last section of Chapter 7, we're going to be taking stoichiometry concepts and applying them to 3 lab techniques: titration, gravimetric analysis, and combustion analysis. Our first technique is titration. In titration, we're using a known amount of one of our reactants and the stoichiometry of the equation to find the concentration of the other reactant. Let's go over some definitions. The titrant is the substance that we know the concentration or amount of. The analyte is the substance we're trying to find the concentration of. We are analyzing it. The equivalence point is the point in the titration where the moles of the titrant, that is the substance of known concentration, equals the moles of the analyte, the substance of unknown concentration. For acid-base reactions, it's going to be the point where the moles of H plus from the acid equals the moles of OH minus from the base. We use an indicator for our titration reactions, which tells us that we are at or near the equivalence point, and it tells us this by changing color. In a typical general chemistry lab experiment, phenolphthalein is used as the indicator. Phenolphthalein turns pink in the presence of excess base, which is very near the equivalence point of the reaction between acetic acid and sodium hydroxide. The end point of the reaction is usually close to the equivalence point, but not exactly. The end point is the point you stop the reaction. It is going to be the point at which the indicator changes color. Hopefully it's changing color very close to the equivalence point, but it may not be the exact same point. For example, with acid-base titration using phenolphthalein, the equivalence point is when the acid and base are in equal amounts. But the pink color comes when we have 1 drop too much of base, so there's excess base. That means for titration using phenolphthalein as an indicator, the end point is 1 drop beyond the equivalence point. Here's an example calculation for a titration. We're told that we had a 50 milliliter sample of hydrochloric acid. When we got to the end point of the titration, 35.23 milliliters of 0.250 molar sodium hydroxide had been added. We're also given the equation for the reaction. HCl aqueous plus NaOH aqueous yields NaCl aqueous and H2O liquid. We want to find the molarity, that is the concentration of the hydrochloric acid. The heart of this problem is a mole-to-mole conversion from one substance to another. But before we can do that, we have to get our known concentration into moles. We know the molarity and volume of our sodium hydroxide, so we can use a rearranged version of our molarity equation to find moles. Then we'll go from moles of the sodium hydroxide to moles of HCl using the balanced equation. Lastly, we can combine moles of HCl with volume of HCl using our molarity equation to find concentration of HCl. First of all, we're going to have to get milliliters of sodium hydroxide into liters. Anytime we use our molarity equation, the volume has to be in liters. We take 35.23 and multiply by 10 to the minus 3, and that gives us 0.03523 liters of sodium hydroxide. Once we have liters, we can plug it into a rearranged form of our molarity equation. Moles equals molarity times liters. Our molarity was the 0.250 molar sodium hydroxide, and liters of sodium hydroxide was 0.03523. We're multiplying those together and get 0.088075 moles of sodium hydroxide. Moles are often going to be a small number like this. Then we're going to use stoichiometry to convert from moles of sodium hydroxide to moles of HCl. In the equation for the reaction of HCl with sodium hydroxide, there was a coefficient of 1 in front of the HCl and a coefficient of 1 in front of the sodium hydroxide. If that were not the case, we would have different numbers in the stoichiometric factor. Our number ends up still being 0.00888075, but now we're talking about moles of our acid, the HCl, instead of moles of the base. We can take our volume of our acid and change it into liters, since we're about to use our molarity equation a second time, this time related to the acid. The first time we used it, it was related to the base. Now we're using it related to the acid. We change 50 milliliters into liters by multiplying by 10 to the minus 3 and get 0.05000 liters. We plug our numbers into our molarity equation. Molarity equals moles over liters. There are 0.0088075 moles of HCl. There are 0.05000 liters of HCl. We do 0.0088075 divided by 0.050000 and come out with 0.176 molar HCl as our concentration. Automobile batteries use 3.0 molar sulfuric acid as an electrolyte. How much 1.2 molar sodium hydroxide will be needed to neutralize 225 milliliters of battery acid? That is, the 3 molar sulfuric acid. H2SO4 aqueous plus 2 NaOH aqueous yields 2 H2O liquid plus Na2SO4 aqueous. Remember to do the stoichiometry step in the middle based on the chemical equation. It's going to be important. Is the answer A, 0.045 liters, B, 0.56 liters, C, 1.1 liters, or D, 0.90 liters? The correct answer is C, 1.1 liters. We start with the moles that we can figure out, and then do a mole-to-mole conversion for the thing that we don't know yet. The moles that we can figure out in this case are going to be based on the sulfuric acid. We have a known concentration, which is 3 molar, and a known volume of the acid, which is 225 milliliters. We change milliliters into liters and plug it into our rearranged form of the molarity equation. Moles equals molarity times liters. That will give us moles of acid. Then we go from moles of acid to moles of base using the balanced chemical equation. Notice there's a 2 in front of the sodium hydroxide. That has to go into our conversion factor. Then we can go from moles of our base, sodium hydroxide, to the volume of the base, since it's asking how much will be needed, and all the answers are in liters. We know a molarity and we know moles now, so we can solve for liters and come out with 1.1 liters.